Hello, welcome everyone. Feel free to say hi if you're here. I hope everyone's good. Hope everyone's well. It's a very hot weekend where I am, so the temperature's kind of certainly signifying the start of summer. I hope you're all well. It'd be great to hear from people in the chat, so do feel free to say hi if you have joined and ask any questions, share answers as we go today. That would be great. Hiya. Oh, welcome. Oh, that's great. That's great to hear. I hope you're well. Thanks for joining. And it's lovely to see comments in the chat and hear where people are sort of joining from as well. So that's lovely. I hope you're doing well. Let me know if this is a topic you've done before. So we're looking at disguised quadratics. So very much the A-level style of quadratics where the questions are a little bit more involved and they're not so obvious. So we use like a substitution and stuff. So this would be a really good topic to look at today, the kind of harder, more A-level style uses of quadratics. So I'm keen to start, but welcome to anyone else who's just joined. Do feel free to use the chat today. It'd be great to hear from you. Questions and answers as well, and comments on this topic. But yeah, welcome and thank you for joining so promptly. I'm going to start sharing what we've got in store today. So hopefully you'll be able to see the screen now. I'm just going to make it full screen so we can get started. But I can still see your comments and stuff. So do feel free to say hello, share answers as we go. And hopefully you can now see the title page on Disguised Quadratics. So we'll make a start, but welcome to everyone. And I hope you're having a good weekend. Cool, so can we all see that? Do feel free to use the chat. I'm going to make a start. So, disguised quadratics, this is very much an idea that's explored in year 12 and 13. But we're gonna have a little look at some of the different flavors of questions we can have for this. Yes, so for those halfway sort of through the A-level, this year's exams have taken place, but for those in year 12 that have kind of done half of the A-level study, this will be carrying on, and this will be a topic that a lot of students have probably covered this year, but will grow in year 13 as well. So if you're sort of halfway through your course, this is hopefully very beneficial for you. So just very quickly, I'm Max, I'm head of maths at Snap Revise. I did a maths degree and basically have been teaching GCSE, Key Stage 3 and A-level ever since. So that was a few years ago now. It's been an interesting time to be teaching with the changes in exams and the changes sort of across the world in that time. But yeah, there's a lot of good content to get through today. So we're going to be looking at equations that have quadratics to them or elements of them that are disguised. So it's a really good topic that builds on GCSE and is going to be used in all sorts of different parts of maths from here on out. So they're really good to be able to spot these techniques and feel confident with. Hi, welcome. Lovely to hear from people. So as I said, this is very much pitched at those still working towards their A-levels. So for next year, and we're kind of continuing with that for students getting ahead of the game a little bit, but this is something you're likely to have covered in year 12 this year. It's certainly very warm today. Yes, where I am, definitely. So we're going to have a little look at this just as a kind of prerequisite idea. I'd like to just go through and use the sort of standard coefficients that we use, A, B, and C. And hopefully we recognize what these techniques mean. But the discriminant, has everyone seen that before? Going to give it a little symbol, but we talk about this as b squared minus 4ac. This is a really important part of the quadratic formula that actually tells us a lot about the quadratic. If you know what the use of this is, please let us know. Yes, well done, absolutely. So the discriminant is b squared minus 4ac. So for the particular case of this quadratic, that would be 7 squared minus 4 times 3 times minus 6. And so if that comes out as a positive number, which I believe it does, that's going to tell us that there are two solutions, because any positive number has a plus and a minus square root. So the whole point of the discriminant is it actually tells you how many solutions this has. Well done, excellent, and thanks for that comment there. So hopefully this is just the recap bit. So if it's greater than 0 or positive, that's telling us 2 solutions. I'm just going to abbreviate that. If it's equal to 0, that tells us there's 1 solution. And if it's less than 0 or negative, that tells us there's no real solutions, no real roots. And hopefully this is something that some of you have seen before. And do let me know if you've seen this before. I can tell from the chat that some of you have. Welcome if you've just joined. It's lovely to see so many people join in today. So yeah, we're going to take quadratics a lot further in this session, but I'm just doing a very quick recap. Hopefully we're quite familiar with factorizing. This is probably one of the earliest skills we look at with quadratics. But the whole point of it, again, is for it to tell us the solutions. Hi, welcome if you've just joined. We're just doing a very quick recap, and then we're going to get on to some very involved quadratics, and hopefully that'll be useful for everyone. The quadratic formula, now interestingly, this year on the GCSE, they gave this formula. By A-level, I think we're very much expected to know it, but also a lot of the calculators that are allowed now, you almost don't need to worry too much about the quadratic formula because a lot of them just solve the quadratics when you type it in. So quadratics are a kind of really key idea, but we're going to be looking at the harder applications of that today. Welcome. Yeah, right. So completing the square, that's a really good point. It is a little bit nasty when the coefficients aren't 1. So thank you for that comment, who's that, Bradley? Yeah, when the coefficient isn't 1, it is a little bit more involved. And what I would personally do is I would probably take the 3 out and have x squared plus 7 over 3x minus 2. And then what you do with this is you complete the square on this little bit here. So we get an x plus 7 over 6 squared. You've got the 3 out the front. And we minus 7 over 6 all squared, which is 49 over 36. And we still have a minus 2. And it does already look much nastier. So please do let me know if you've seen this before. But actually the solutions will still work, because if we divide both sides by 3 and rearrange, we get x plus 7 over 6 is equal to, and if I tidy that up, move it across and root it, I'd get plus or minus 11 over 6. And if I minus 7 over 6 from that, I would get x is equal to minus 3 or 2/3. So completing the square is a little bit trickier when the coefficient isn't 1. I completely agree with you there. But that's something we could maybe explore further on in this video. What we are going to be looking at, though, is this sort of sneaky disguised quadratics. But that's lovely. That's lovely to hear. And it's lovely to hear that you're kind of aware of what techniques are perhaps more beneficial in different circumstances. So as I've said, for all the A-level exam boards, and those of you that are in year 12 or working towards your A-level still may have come across a lot of this already. But quadratics build and build. And here's an example of one that is quite involved. And involves what we'd call a substitution. So who has seen this technique before? So I would personally use a substitution here. Some people are maybe more confident with just dealing with it as it is. I personally like a little substitution. Superb suggestion there. So let's let y equal, and for this one, I would probably say x cubed maybe. So there's sometimes where it's a quartic where it's x to the 4, I would use x squared. But we're going to let y equal some function of x. Okay, so e.g., let's let y equal, and I would say x cubed because it sort of sorts that out and sorts that out as the sort of squared version of it. So that was a really nice suggestions. That's what we need to do. We need to use a substitution. Sometimes it's x squared, sometimes it's x cubed, sometimes it's something really random, like it's totally different. And this is very much a skill in itself, spotting what would be the best thing to substitute. So hopefully everyone's happy here that x cubed squared is x to the 6. So that x cubed as the y, works quite well. Struggling with the pen here a little bit. So this will become y squared plus 3y minus 14 equals 0. And that's a lot of a more kind of obvious quadratic scenario to deal with. It still doesn't necessarily factorize nicely. So you can use your calculator, you can use the quadratic formula to get a sort of an exact answer for y. I'm going to do this now. And I believe y will come out as 2.53. Do feel free to work ahead of me. Or minus 5.53. Now, what do we need to do here? We've solved it for y, but we weren't actually solving a question that used y. We invented y ourselves. So what do we need to do at this stage? We actually want solutions for x. So what we're going to need to do is, is take our values of y and think about the substitution. Y equals x cubed, so x is the cube root of y, excellent, or the third root, the cube root of y, that's lovely. So cube root of y, which ends up being 1.36. Again, you're obviously not expected to sort of do this in your head. That's great. Yeah, so we want to go back and find x by undoing the substitution at the end. So we created ourselves a nicer, more obvious quadratic, solved it for that new variable, and then put it back in terms of the thing we wanted. So that was really, really good. Well done, guys. We're going to keep going. Do, as I said, feel free to share any questions and answers as we go. Sorry about the formatting with this one. I'm going to maybe rewrite this random bit down here. 4x minus 2 to the 10 minus 12 lots of x minus 2 to the 5 plus 9. So we can determine the number of solutions of a disguised quadratic by basically finding the discriminant. Good. Excellent. Finding the discriminant. So this time, actually, guys, we're not asked for the solution. We're asked for how many solutions potentially. So the discriminant, remember, was the b squared minus 4ac bit. Now, what would the substitution be here if we were to solve it? Because this is very much a disguised quadratic. It's something lots of x minus 2 to the power of 10 minus something lots of x minus 2 to the 5 plus 9. So hopefully that we can see that if we used a substitution, very good if you're working sort of ahead of me, but the substitution we would use to solve it would be that. Does everyone agree that it sort of comes from this bit, and that would be the squared version of it? Yeah, so this time, instead of, because it wasn't to the 6 and the 3 like last time, it's this random thing to the 5 and the 10, you would use the thing to the 5, sorry, not x minus 5, that was my mistake, x minus 2 to the 5, because then that effectively becomes minus 12y, and that becomes like 4y squared, because anything to the 5 raised to the 2, you times the powers, and that would be to the 10. So that would be like the quadratic that this would boil down to. Yes, yeah. And I made the mistake there as well. I think there's a lot more going on. It's easy to write the wrong number in the bracket or the wrong power, but absolutely that's the bit our attention is sort of drawn to. So very good, well done, and thank you for everyone's input. This is brilliant. And now, so this is the quadratic that it boils down to. We're not, again, being asked to solve it. We're just asked how many solutions. So what we can do here is absolutely, I think someone suggested it. No, that's fine. No worries. I think the suggestion was brilliant. We need to use the discriminant. Again, did anyone notice that? Yeah. So we need to use the discriminant here to work out how many roots it has. So I would do minus 12 squared minus 4 times a, which is the 4, and the c coefficient, which is 9. And so this actually equals 144 minus 144, which is 0. So does anyone remember with the discriminant how many solutions that implies it has if it is equal to 0? So this tells us that that problem has how many solutions? It tells us it has one. Well done, one solution or one root. So one solution. And actually to find that solution then, what can we do? We can think about, well, when we find the solution of this, we know that the solution of x will just need to be the fifth root of it plus 2, because we're solving for x minus 2. So it's a repeated root. Yeah, so it's a solution that's repeated because of the discriminant. Really good. So that's applying what we know about your bog standard sort of quadratics to this. Very good. Excellent. So here's another nice one. And again, this depends very much on how much of the A-level sort of pure content you've seen, or how much of this pure maths you've been exposed to in the past. But now we're dealing with an exponential or potentially a log problem. Very good. Yeah. So for this one, again, it is a disguised quadratic, but it takes us to sort of use our knowledge of index laws and powers to see this, because hopefully everyone's happy that e to the x to the 2 is the same as e to the 2x, because you times the powers. But that is also like something being squared. So in this case, this is the scenario whereby we would let y this time be an exponential and equal e to the x. So we would have, let me just check. Yeah, we've carried on from there. So what we would have here is this would be like y squared plus y minus 6. Yep. And that's equal to 0. Superb. And again, this then boils down to a very sort of manageable quadratic. That is not as daunting to look at as that. This is something we're way more familiar with and something we can solve. So what would we do here? Let's have a little think. Well, this one actually, I can tell you, does factorize. Do feel free to work ahead of me if you can factorize it. And then we need to think about how we solve this. This is a really, really good one to look at. So y squared plus y equal, minus 6 equals 0. Can anyone tell me how that factorizes? Or you might just know how to solve it quite quickly. But I've kind of given you a hint that it does factorize. So y squared plus y minus 6 equals 0. What are the solutions for y? What are the factors? How do we deal with this one? My hint. Okay, I just got a notification about the mic. I'm hoping that didn't cut out there. But anyway, let me know if you do know how to factorize it. Very good. Oh, excellent. Thanks for the suggestions, guys. So y minus 2, y plus 3, which actually gives us the roots. Y would then equal to or minus 3. Is everyone happy with that from those? So they're the factors. But when you then take the roots from them, you have to make the bracket equal 0. So when y is 2, that bracket would be 0. The whole thing would then equal 0. Or when y is minus 3. Now that isn't, of course, the final answer, because we now know that that tells us e to the x is equal to 2 or minus 3. Right. So any interesting comments here? Because we still haven't fully solved for x, but you guys might have observed something here that's worth pointing out, because we're dealing with a much bigger idea now. E to the power of x equals 2, or e to the power of x equals minus 3. So this is brilliant, and the comments have been superb. We're really teasing out the key sort of methodology of this, but this final stage is really quite crucial. E to the x equals 2, or e to the x equals minus 3. What do we have to also be really careful of? Right. Very good. If you take natural logs of both sides, that's superb. X is natural log of 2, and that is only that one. Why is that? Why is that the only solution? Because that quadratic in y did have 2 solutions, but there's only one solution for x, and that is the natural log of 2. Excellent. We can't take log of a negative number. E to the x can never be negative. And if you know what the e to the x graph looks like, an exponential graph, it has an asymptote at 0. So that graph isn't defined below 0. That's not in its range. So you can't ever have e to the x equaling minus 3, because it won't ever happen. So that won't have any solutions. So that leads you to a dead end. Brilliant. And you guys have explained that really well. There's different ways of saying it, but yeah, basically e to the x can't be minus 3. And also you can't take log of a negative number. So that is brilliant. And this is very much now how it's been taken into the realms of A-level, because what has a kind of quadratic equation at the heart of it has all these other branches and bigger ideas sort of coming off of it as well. So really well done. Just a little checkpoint. If you could just give me a 1, 2, or 3 on how confident you're feeling with that stuff. And then we're going to push on to some more wacky abstract ones. Excellent. That's great to hear. Thank you, Bradley. That's brilliant. Looking at the comments and the chat and the questions and the answers, it does look like most people are sort of fairly confident with this, although we've hit some tricky ones now. Yes, absolutely. If you've got any questions you want me to backtrack, please let me know. We're going to push on shortly, but there's no rush. I mean, we're working through this really efficiently. What would you like to ask? Was there something on here we needed to check? Do let me know. Brilliant. Yeah, feel free to update me on how confident we're feeling. We are obviously doing much higher level stuff than just bog standard quadratic. So don't worry if you feel like it is quite challenging. Oh, very good question. No, I think in general, it just needs to be clear that you have solved it and then ignored it. So it doesn't hurt. You won't lose any marks for saying a reason. But as long as you actually do ignore any that aren't valid and you make that clear that you've chosen to ignore them, you don't necessarily have to say why. Unless there was a sort of a follow-up comment question that said, give reasons why you've ignored solutions. I don't think I've ever seen that. They could ask you to comment, but in general, no. Yeah, so there's no harm in doing that, and it doesn't take a lot of writing. So it's absolutely fine if you want to. I think it's nice to be very clear about stuff. So a little comment, ignore, and maybe a quick reason if you want is fine, but that shouldn't cost you marks as long as the right final answers are all there and no extra ones, you'll get the marks. Brilliant. So this one here, this is an interesting one. Hopefully you guys can see the full question. So it says solve the equation x minus 6x to the half plus 2 equals 0, giving your answers in the form p plus q or minus q root r, where p, q, and r are integers, meaning whole numbers. This is a really good exam question. Again, this is actually a disguised quadratic. Any ideas what would be an appropriate substitution here? Welcome. Hi, welcome if you've just joined. And anyone that wants to comment with answers, solutions, suggested methods here, please do feel free to dive in and do that. What would we use here? Superb, absolutely right. Brilliant suggestion. Y equals x to the half. Y equals x or to the 0.5 to the half. And that will actually transform this scenario into a quadratic. Because if y equals x to the half, then x to the 1 is like y squared. So this whole thing here would become y squared. Yeah, superb. Brilliant answers coming through or suggestions for this. And then it's a more obvious quadratic, which again, we can look to solve. So to mix it up, let's do this one as a complete the square. Because you could use the quadratic formula, but solving by completing the square actually gives you it in a sort of surd form anyway, because that's sort of implying to us that it doesn't factorize nicely. And this is where we can use the question to our advantage. So what we can do is we can go y minus 3 squared minus 3 all squared, which is 9, plus 2 equals 0. Tidy that up, we get y squared minus 3, y minus 3 squared minus 7 is 0. If I rearrange that, then y equals plus or minus root 7. No, it doesn't. Y minus 3. If I square root both sides, and then I need to add that across. Okay. Now, is that finished? Because it sort of looks like that. But yeah, brilliant up to here. We're doing really well because this is already the kind of problem people won't see as a quadratic. So the fact that you guys have not only spotted that it is, but also chosen an appropriate substitution. No, we're not done. We need to solve for x. Brilliant. So we're kind of like halfway, but we've probably done more than half of the work. So solving for x, what we're going to do is remember that if y equals x to the half, x is equal to y squared. So I can find the x values by squaring my answers. And that's what's different. That's what's perhaps maybe not as obvious. So I'm going to do what? 3 plus root 7 squared, or 3 minus root 7 squared. Now that is it. They are the answers. But remember, yes, superb. And I think I would have struggled to maybe get this the right way round in the pressure of an exam, because you sometimes get a little bit like, oh, I'm nearly there, and it gets a little bit rushed. So you have to actually square to get this substitution rather than like square root or something. So we've got to be careful that these are also sneaky double brackets. So we need to expand that as 2 brackets of 3 plus root 7, 3 plus root 7. And then equally, we need to do 3 minus root 7 and 3 minus root 7. And I believe that if we do that, we get 9 plus 6 root 7 plus 7, not 49, root 49, or 9 minus 6 root 7 plus 7. So that means that the answers for x is equal to 16 plus or minus 6 root 7, which of course is in that form we wanted. P is 16, Q is 6, and R is 7. So do feel free to screenshot, feel free to ask any questions, feel free to ask me to repeat anything if we need to check, but we can see this is very much an A-level question. It's got surds in it, it's very sort of pure mathsy, and it's probably also one of those ones that a lot of people would like struggle to get started with in an exam. They'd kind of see it and think, oh no, I don't know where this is going, and then maybe move on or spend too long looking at it. But once we've done enough practice, enough sort of breadth of practice of this sort of thing, it's actually okay. Good. So do let me know if at all you want me to move back. We're going to do another exam style question here, and then we'll move on. Again, feel free to work ahead of me. We've got another disguised quadratic now. 7 to the 2x minus 4 lots of 7 to the x plus 3 equals 0. So please do suggest any substitutions that you think might be the best ones to use here. And I often say try and be governed by the sort of middle term that doesn't look like the squared bit, that looks like the actual x term. Yes, right, brilliant for noticing that this is like 7 to the x to the 2. So that's the thing that's being squared. So that's actually the substitution we want to use. Very good. So let's let, not x, let's let y equals 7 to the x. Don't have to use y, by the way. You could use any letter you want. You could call it u, any substitution that's maybe a different letter from x. So that would then create for us the quadratic problem of y squared, because it's 7 to the x to the 2, minus 4 lots of y plus 3. Again, it suddenly looks a whole lot nicer, a whole lot more sort of manageable. And again, guys, it's something that does actually factorize. Very good, superb suggestions. And this question is telling us 2 decimal places, but remember, we're not finished yet. So very well done. And do feel free to continue to share answers and comments in the chat. Does this factorize? Can anyone factorize this for me? Let me know where we could go with that, and get our solutions for y. And then remember, we are actually solving for x. So has anyone got the factorized version or the solutions for y? What does y equal? Brilliant, brilliant work there. It factorizes as y minus 1, y minus 3. And if we can do it in this sort of manageable bite-sized way where we go through, put the answers, it will lead us nicely to the next step. So this tells us that y is equal to then positive 1 or 3. So that's the solution for y. And we invented y to help us solve this problem. Remember that y was equal to 7 to the x. So this is now the thing that we need to sort out and undo. So what do I do with that? Well, if y is 7 to the x, and we want to get x in terms of y, are we all happy that x must be equal to log base 7 of y? So the way to undo an exponential, like a something to the x, is to take the logarithm of that base of the thing. So you log base 7 both sides, and that will give you the sort of corresponding x value. So I think this is the one bit that could make this trickier. Excellent. So very well done if this is something you've seen before. But again, this is bringing in other A-level knowledge, which is why you've got to feel confident and sort of fluent moving between the different areas of pure maths here. So that was really good. And so what we would have is we can then take log base 7 of our various y values that we found. So log base 7 of 1 or log base 7 of 3. Now, these are actually what we'd call the exact answers. As a mathematician, we'd like them better. So it does have to be log base 7 for this one, Bradley. Really good question. Because we're trying to undo a 7 to the power of x. Some of you may have come across the fact that if you're taking logs, if you're solving a log or an exponential equation, there are various ways you could do it using log rules, and you don't always have to take the same, or that you do have to take the same base, but you don't have to do it in a very regimented way. However, for undoing this and using it as an inverse function, you must use log base 7 because you're trying to directly undo 7 to the power of x. So that was a brilliant question. But this question didn't actually ask us for it in an exact form. It actually asked us for 2 decimal places. So log base 7 of 1, that is actually doable without a calculator. You don't have to do it without a calculator. If you can try and use the calculator, but does anyone know what that should be? Log base 7 of 1. Log base anything of 1 will always equal what? Because remember, 7 to the something equals 1. So log base 7 of 1, we're saying 7 to what power equals 1? It's 0. Very well done. And think about the y-intercept of an exponential graph. It's always at 0, 1. Very good. Well done. Now, log base 7 of 3, just use your calculator because it says 2dp, would be 0.56. So these are our 2 answers to 2dp where appropriate, meaning one of them actually was just 0. And that makes that sort of make a bit more sense as well. So this was like a full-on question, very much an exam question. But excellent comments, excellent ways of challenging this. I'm glad that you guys challenged this in the chat and asked if this is appropriate and so on. So what we're going to do now, this is a nice bit of an extension on what we're doing. We're going to do some trig ones, and then we're going to look at some weird quirky questions as well. So find all the solutions of 2 sine squared theta equals cos theta minus 1 in the domain 0 to 360 for theta. Now, straight away, this looks suddenly way more complicated because it's involving trig. What we're going to do first of all is we need to use here trig identities. So hopefully we've all seen the sort of 2 main trig identities that we use in year 12. Can anyone suggest what we might want to change here? Now, I think this is the thing that's restricting us. So we're probably going to want to change this, but how are we going to do that? Superb. So there is an identity connecting sine squared and cos squared. Sine squared plus cos squared is always identically equal to 1. So that means that we can replace sine squared with 1 minus cos squared. And this is definitely the way to go, because then we just got cos everywhere. Okay, and we've not got to worry about dealing with 2 different trig functions that are doing different things. So if I expand that out, I get 2 minus 2 cos squared theta equals cos theta minus 1. And I can bring this all to one side and get a more obvious looking quadratic. So I'm going to plus the 2 cos squared theta across because I prefer positive quadratics. Move that over here. And so it'd be 2 cos squared theta plus cos theta And then if I minus 2 across from the minus 1, I'm going to get minus 3 equals 0. And then absolutely use the substitution again. I'm going to let y equal to cos of theta. So the quadratic I'm left with here is 2y squared plus y minus 3 equals 0. And this actually does factorize again. Brilliant suggestions and comments in the chat. Apologies if I'm going too quickly, but do slow me down, ask, and also at the same time, feel free to work ahead of me here. Now we're going to factorize this as 2y plus 3y minus 1. And even if it didn't factorize, you can use your calculator to just solve it. But very well done. Yeah, excellent if you factorize that. So what that tells us is that y, actually I'm going to give myself a bit more space. Apologies for sort of flitting all around the screen, but I want to make sure it's clear. So just do ask if we're not sure. So y is minus 3 over 2 or 1. Now remember, y was the substitution for cos theta. So cos theta could equal minus 3 over 2 or 1. Are either of those a problem? Very good answers, guys. That's superb. I'm not slowing down here. I'm going quite quick, and you guys are certainly keeping the pace up. But if you are unsure about anything, please do let me know, and we can go back. Anything here that we noticed that's a bit of a problem? Yeah. Very good, brilliant comments, and lovely sort of supportive comments there as well, because this is getting quite involved now. This is not possible. Cos theta can't ever equal minus 3 over 2. If you try and inverse cos that in your calculator, it will say math error, calculator error, because cos is only defined between 1 and minus 1. So if you do arc cos or shift cos of that, it won't work. So we're only dealing with cos theta equals to 1. So that means that theta is equal to inverse cos of 1, which would be 0, the principal value your calculator will spit out, and also 360. Now we need to know where to look for other solutions. But if you're familiar with the cos graph, you'll know it looks like that, and it peaks at 0 and at 360 at 1. And since this includes both 0 and 360, it's mad. We've really literally stretched it to the limit here. We've used the bounds. The solutions are right on the boundaries both times. So that's brilliant. Yeah. Oh, I'm just looking at the question. Oh, yeah, no, that's fine. Sorry, really good questions. And what I really like is you guys are asking very specific things about exam technique. If you do skip writing let y equal this, that's absolutely fine. If you can see how the substitution should form, or you can factorize it without, no problem. But just make sure that for the harder substitutions where it was like you had to square it or square root it and then add something or whatever, that you undo it correctly. And I just personally find it easier if the substitution is written really explicitly somewhere, you can sort of run from that, because it's the final stages, again, people mess up, not necessarily because that they're rushing, but because it's a little bit more convoluted than just a simple way of undoing it. And it just helps. I find it helpful to have the substitution written, but no, you don't have to spell that bit out. That's fine. That's great. Well done with that. Now we're going to do some really quirky ones. I like these problems. I've seen a similar one from the Cambridge Maths Hub. They did this sort of problem. I don't know if it was used in an Oxbridge entrance exam or something, but it's actually really cool because the maths isn't as bad as it looks. So we look at this problem and it's like a quadratic to the power of a quadratic. And everyone thinks, oh my goodness, this is like really involved. But there's a really nice way of doing this. And so I think this would be a really good thing to sort of look through, to kind of push the boundaries of what we know and then actually appreciate it for not being too bad as a problem. So we've got a quadratic to a quadratic, and we want to find how many, like all the different solutions of when this would equal 1. So what I would suggest is let's think about when something to the power of something is equal to 1. So the cases we're going to use, I'll just write these out quickly. and then I'll answer any questions that have come in the meantime. But yeah, no, thank you so much for the input today, guys, and the questions. So I'll answer that one in a sec. I think we'll have plenty of time at the end as well. I'll just get through these last couple of questions, but if I've missed a question, feel free to resend it towards the end. So case one, brilliant. The cases are that the scenario that anything to the power of 1 to the power of anything is 1. Okay. And also something to the power of 0 is 1. So I'm going to start with this. Does everyone agree that 1 to the power of anything? I think you guys have actually all started with the harder scenario or the other scenario we're going to do in a minute. But I'm going to this is the bit people forget. This is why I want to talk about this. Does everyone agree that 1 to the power of any number is always 1? 1 to the minus 10, 1 to the 8th, 1 to the minus 1, 1 to the 0 is 1. 1 to the power of anything will always be 1. So with that in mind, if this bit equals 1, then we've got some answers already. So there's probably, there could be like loads of different answers. So this is x squared minus 3. If we rearrange it, equals 0. So x would equal, basically, x squared equals 3. So x equals plus or minus root 3. So there's two answers already. X equals minus root 3 or root 3. Now, the other suggestion some of you guys came up with, let's move this on. Case 2, what did we say is the other scenario where something to the something equals 0? Any suggestions? Yes, let that bit equal 0. Very good, because anything to the power of 0 is 1. So what that means is that this weird bit, now that's something to solve, and that in itself is a little bit tricky. Good. So for this bit, this again is a sort of sneaky one, because this is like x squared minus 6 minus 8 over x squared. Now we could do a substitution, or we could actually take out a factor of 1 over x squared. And then we've got x to the 4 minus 6x squared minus 8. Oh, I've just looked at the question. I think there was a mistake in the original question. I think it should have been a plus. Sorry, I don't like doing that, but I want to make sure this actually works. But I'm going to just pause here because this was a little bit tricky. Does everyone see what I've done? By factoring out a 1 over x squared, I've had to compensate for that everywhere else. So that's what we've got. And now what we could do is we could let y equal x squared. And so what we would have is we would have 1 over y brackets y squared minus 6y plus 8. Now, please do ask if you're unsure about any of this, because this has suddenly jumped up. Good. And then this would become 1 over y minus 2, y minus 4. And so y could equal 2 or 4. Y equals 2 or 4. So x could equal the square root of both of those. So x could equal plus or minus root 2. Square root of 4 is plus or minus 2. Or from earlier, plus or minus root 3. So quite a lot of different answers there. So well done if you got that. If there's any questions, let me know. Very good. Excellent. And thank you for the comments and questions in the chat as well. Just a little, yeah, no, I feel the same. Sometimes it's very easy for maths to be like all over the place. We've got to try and keep it logical and clear and sort of flowing. But very good. So just a little update on how you guys are feeling with that. And then we'll do a couple of exam questions to sort of bit of final practice for the real way that this could come up in a A-level exam question. Brilliant, excellent. No worries. Now that was significantly harder. I think that took a bit of almost being a little bit creative with it there. So please do feel free to give an honest opinion on how you found that. It's good for us to know. The other thing that does need to be said though is we can't sort of shy away at A-level maths from hard questions. So although it's tricky, it's really good to sort of power through and make sure you see these problems through and do challenge it when it's tough. Yeah, exactly. And I think that's what holds people back in the exams, is that the sort of worry of trying stuff or not having done a breadth of practice actually sort of is the detrimental effect, is that it costs people time. And that is not knowing where to start, that sort of thing. Yeah. So let's have a little look at this one. Given that y equals 3x squared, show that this is the case. Okay, so this is just a first question, whereby I would say we probably want to just take logs of both sides. So here we go. If we do part A, I would say if you take log base 3 of both sides, log base 3 of y equals log base 3 of 3x squared. If anything, this is a test of log rules. Are we happy that that's the same as log base 3 of 3? Which is equal to that. Log base 3 of 3 is 1. And then the 2 can come down as a power. So this was just like a part A random thing. Then it's actually going on to ask us to solve something else. So we're being asked to solve this equal to this. Now what you might think is, where's the link? Why is it saying hence? What's the link to the previous part? Well, I know that this is the same as this sort of thing. So no, that's fine. And do you know what? I actually just thought there, we've kind of just dived straight into a logs question and not done any of this stuff today. And you might think, wait, how do I do this? Because it's a totally different skill. But don't worry if you think, oh, that kind of caught me off guard, that first bit. Yeah. So what we can do is we can sub our previous answer instead and say that log 3 of y, so log 3 of 3x squared, is effectively this. And that is being equal to log 3 of 28 minus 9, sorry, 28x minus 9. Now, guys, actually, this is where we can overcomplicate it and we don't need to. Because it's log base 3 of something equals log base 3 of something, are we happy that at this stage, the two somethings can just be equal? So we can just take them out of logs. So we can literally at this stage say 3x squared must be equal to 28x minus 9. And there we are, we've got our quadratic. So we've got 3x, and people go, wait, how did you get that out of logs without raising to a power? Because it was log of something is equal to log of the same something, and you can just equate them. You just remove the logs, exactly. So then here, this, I believe, factorizes. So it wasn't so much sort of substitution-y one. It was just one where you had to spot the link to part A. Yeah, so some of these marks, I suppose it depends. But yeah, yeah, is that all right? Yeah, no, it's actually not that bad in the end. But if you don't spot where to go with this, again, it all comes down to practice. And I know people hate hearing that, but once you've seen a question like this a couple of times, you can go, right, it's only this many marks, so it's probably not want me to go through all this work. Is there a quicker thing I could do? Can I use the part A answer? Can I just say two things are equal to each other? And that's what we need to be looking for. Right, let's do another one. Do feel free if you need me to backtrack. But yeah, the comments and questions and answers have been brilliant today. And thank you all for that. Because what sounds like, you know, quadratics, we've been doing this forever in GCSE, we've dealt with some really big problems. And again, here's another one. So this one here, 4 cos squared. Are we happy that we can write that as 1 minus sine squared x plus 7 sine x minus 7 equals 0. So if we expand that out, it's very like actually the one we did earlier. Do feel free to work ahead of me. Oops, plus 7 sine. I'm going to bring it to the other side because I don't like having a negative sine squared. And then minus 7 plus 4 is minus 3, but I'm bringing it across positive 3. And then I'm going to let and again, that will factorize. Yeah, I actually don't like negative coefficient quadratics, and I do agree. Even if you're putting that into your calculator, it's like you prefer looking at it when it's a positive quadratic. I completely agree. But no problem. Yeah, so y equals sine x. So we know, hang on, what have I done there? That was kind of not factorized it at all. So that should be a 4y minus 3 or y minus 1, I believe. So then we've got sine x equals 1 or 3/4, which are both feasible. And if we solve that for x, we get 90 degrees, 48.6 degrees, and 131 degrees. This is now solving like a trig equation type problem. So that was a good one to do. But we can see very quickly it gets beyond just dealing with a quadratic to then being, right, now it's a trig equation, now it's an exponential, and so on. So these are good, and we are really powering through some tough questions here. I'm aware that people had other questions as well for me that they might like to ask. I think we've got one more we're going to look at, and then if there's anything else you want to check, I'm happy to do that. So this one here, yeah, lovely, brilliant answers. That's superb. So this one again is a very sort of log-based one. Now, don't forget, where did 6 come from? Oh, maybe the rounding was, maybe that's not right. Was it sort of bang on? Maybe it was just 48. Let me just check. That wasn't 6, it was 0.6. So yeah, yes, yeah. So this one here, don't forget that log of a number, like log base some number of another number, is just a number. So log base 2 of 32 is actually literally just a number. It's one you could probably work out without your calculator. If you say, right, 2 to the power of what is 32. So this is just a really complicated way of writing 5. And this one here is a really complicated way of writing 4. So they've kind of just made this look more logsy than it really is. This is what we've got. We've got 9 over log base 2. Now we need to be careful here, because if I times up by log base 2 of x, 9 equals log base 2 of x all squared. Now people confuse this. This is not a log rule where you bring the power to the front. That's where we need to be careful, because it's not in the log. Don't think that's a word, but hopefully you know what I meant. Good. So what we're going to do here is we're going to use substitution at this stage and call it y squared, because the log rule doesn't really apply, because it's not log 2 of x squared, it's log 2 of x all squared. So we need to be sort of kind of careful with that. But by using the substitution that y is equal log 2 of x, this is doable. So that means that y is equal to plus or minus 3. So that means that log 2 of x is equal to minus 3 or 3. And that is actually feasible because 2 to the minus 3 is an eighth and 2 to the 3 is 8. So that means that x equals 8 or 1/8. Yeah, it is a sneaky question. And what's really sneaky about it is that at each stage, there's something we sort of want to do, but it isn't that. It's not, that's not the thing it's getting us to do. So you want to use log rules, but it's not, you need to use substitution. You want to then go, right, log 2 of x, you want to sort of log both sides and think, I can't do minus 3, but you can do minus 3 because 2 to the power of minus 3 is x does work. So that was a really good one. And they were our final answers. So I think that's it for all the practice. I know a few people had a couple of questions there as well. I'll just wrap this up. But what we've done there, we've recognized given equations are quadratic, looked at the number of solutions, the idea of the discriminant, and solved some really complicated problems. Thank you so much for brilliant questions, brilliant comments, and brilliant answers throughout. We are going to continue to do these sessions on Sunday, and obviously there's loads of resources on the Snap Revise platform. So it's an absolute pleasure working with students like yourselves that are, really pushing forward to excel at the A level. That's brilliant. Oh, excellent. That's lovely to hear. And thank you for taking part so well. It's always lovely to have that engagement in the chat because we've all kind of maybe learned different things in different ways. But actually, we're trying to kind of get this through for the exam sort of prep. And it's lovely to sort of discuss these ideas together. But if you did have any other questions, I can answer those briefly. If you want me to backtrack to anything, I've got a couple of minutes now. Yes, so do feel free to set a reminder on YouTube for the Sunday sessions. On the actual Snap Revise website, like the platform, if you haven't checked it out before, there are weekly web classes and drop-ins which work really well, and there's a summer schedule for that. So if you are interested in those, that we run a lot of sessions on all topics of the A level, and we have drop-ins which will be starting back in September, and it'd be lovely to see some of you there if you are able to join that. Because you then have sort of the back catalogue of videos and resources to really help you get exam ready. And it's kind of a nice interactive way of hitting all the different bits of the A level. So the website's there in the chat. Oh, right. So do I have any advice on make some A level videos next year? Right. So I think the key thing is just anything whenever you're kind of giving instructions for maths, like videos and stuff, I think what you need to do is just make sure you've gone through some nice, clear examples, because the main thing, and it is actually a really good preparation for doing exams, is actually trying to teach it as well. But I would say you need to almost anticipate where people are going to go wrong and what they're going to ask. So as I said, in terms of preparing for an exam, talking it through to someone is actually a really good way to revise as well. And that then teases out any issues. So just really, when you're explaining something, you need to kind of have looked through clear examples yourself and know what the pitfalls would be. So no, over the summer, the sessions, I think the YouTube Sunday sessions will largely be year 12 into 13 topics. On the Snap Revise website, so the sessions we're running every week live, will be year 12 and 13. So they'll be sort of getting you ahead, plus also recapping. So there'll be some year 12 and 13 sessions as well. And we cover mechanics, statistics, and pure. So the weekly web classes I do for Snap Revise include the whole of mechanics, the whole of statistics, and the whole of pure. And we have drop-ins. So if you're struggling with homework or you've got any tests coming up, I know this is more for September, but we have drop-ins which will start back up then. The web classes throughout the summer will be geared up to sort of recapping year 12, but also pushing on to year 13, sort of bridging knowledge. But that's great. And it'd be lovely to see some of you again soon. Thank you so much again. Keep well, keep hydrated, because if you're anywhere like near where I am at the moment, it's very hot. So make sure you're drinking plenty of water. But yeah, thank you again, and hopefully see you at a session soon. Really well done. And yeah, hopefully see you on here or on a Snap Revised web class at some point soon. Thanks, guys. Well done. Bye. Thanks.